So again, so what I'm going to do is we started introduction to convolutional neural network, and we already went through the fundamental operation, how the convolution layers are formed. So I mean, I will quickly go over like those slides today as well, just to keep you in touch as we proceed in this lecture. Okay. So what we're going to do is we are going to first go through this fundamental operation and then talk about like other aspects of convolutional neural networks. So as we discussed, the core building block of a convolutional neural network is a convolution operation or a correlation operation. And the idea is we try to preserve the spatial structure of your input. And as we process your data in this network, we go from volume to volume. And to be able to move from volume to volume, we have to perform this transformation using the filtering operation, for which we use these filters. Okay, so this is just showing one filter, which is actually applied at all the possible locations of this input. And for each location, we are going to get like one response. So we collect response from all the locations to get an activation map. And of course, we have like multiple such kernels. And that's how we go from volume to volume. Okay, so and these kernels actually these kernels actually form a layer inside your convolutional neural network. Right, so once you have this convolution layer, which is nothing but like a set of kernels, and the only parameters are how many kernels you are going to use and what is the shape of these kernels. And then again, using these kernels, you apply a filtering operation on the input and you get the output activation map. And this constitutes like a one layer of your CNN. You can actually stack multiple such layers on top of each other. And again, you are going from volume to volume. So you start from the image, which is again considered as a volume. And depending upon like how many filters you have, what is the shape of those filters, you will have certain shape of these activation maps. And we talked about like how the third dimension of these filters should match the depth of the input volume here. In this case, it's input image, which has 3 channels for R, G, and B. So therefore, we have to match this depth with the third dimension of the kernel. So we don't define that. We only define the first 2 axes for these filters. So that's one point. The second point was the thickness of these activation maps is determined by how many filters you are using in this particular layer. Okay. So for example, in this case, if we are using 6 different filters, the depth is going to be 6. Because for each filter, we are going to like get a flattened feature map. Okay, so those are the 2 important point which should be noted here. And the dimensions, like why we move from 30 to 28, what is the role of like what kind of filters we are using. We are going to cover that later. And then you can see like so one interesting thing I think which we didn't cover last time was, so it's fine, I mean the depth should actually match. So when you're matching the depth, what's happening is when you're placing this kernel at any location, then in the spatial region, you are actually covering 5 cross 5, which means like the 25 pixels which are in the neighborhood, right? But in the depth aspect, you are actually covering all the pixel values, okay, at once. So you're spanning across spatial dimension like X and Y, but you're not spanning across depth. So you're considering all those values just like a single time, right? So all the values are considered when you compute the linear combination of all the activation maps. Okay, so that's one thing to note here.